Hello and welcome back to another HEBI Robotics lecture series. This time we'll talk about homogeneous transforms and forward kinematics. So we have already gone over rotation and translation as separate entities, but what if we combine these two transformations into one linear matrix operation, like with the rotation matrix that preserves the distance and rotation? To do this, we need a general rigid body motion representation. So next, I'm going to set up a situation for this general rigid body representation. So let's take the case of point P, whose coordinates we define relative to frame 1, and we want to find this point's coordinates relative to frame 0. This operation combines a translation of distance and a frame rotation. So we have a representation for the rigid motion, but we want to turn this summation operation into a single linear matrix operation because it will help a lot with frame transformations later. So with some rearranging and padding, we can rewrite this transformation as a singular matrix to represent the translation and rotation of the point. And this 3x3 matrix is known as the homogeneous transformation matrix and is a linear representation of rigid bodies. So let's break down what the homogeneous transform matrix represents. When we expand it out for the 2D homogeneous matrix, the first two rows and columns represent the rotation component, and the third column represents the displacement. The homogeneous matrix can be used to transform points and vectors. Notice the difference in the last columns of the points and vectors. Vectors, which represents the difference between points and do not depend on frame location, have a 0 as the last value in the column, and points have a 1 to represent the translation component. So we can build out multiple compositions of homogeneous transform to represent multiple transformations. First, we start with the rotation from frame 0 to 1, then the translations from frame 1 to 2. To get the transform of frame 0 to 2, we can multiply the two homogeneous transforms together. One thing to be wary of is that the composition of homogeneous transforms are not commutative. That means that changing the order of multiplication doesn't give the same solution. An example of this is shown with these frames transformations. Translation, then rotation, doesn't yield the same end position as rotation and then translation. The main reason for learning all this rigid body motion transforms for easier representation for doing forward kinematics. Forward kinematics is the process of going from robot joint space or the motion of the joints of the manipulator to the task space or where the end effector will be in the world. One of the simplest cases is the planar 2 degree of freedom open chain arm with known link lengths. The number of joints of the manipulator determines the degree of freedoms of an open chain manipulator. First, we're going to analyze this from a complete algebraic perspective. To get a formula for the robot joint angles to the robot task space, we can build out the robot as simple triangles. This visual makes it simple enough to compute the task space and effective position from the triangles to get the x and y position relative to the robot joints. And then we can rewrite this position as a matrix with simpler notation. Now let's find this end effective position using the information we just learned. With the homogeneous transforms of frames, the forward kinematic can be constructed by composing the rigid motion due to the individual joints. So we have 4 frames that represent the motion of the robot relative to the base. These 4 frames are the rotation due to joint 1, the translation of rigid link 1, the rotation of joint 2, and the translation of link 2. To compute the configuration of the end effector relative to the base frame, we concatenate the rigid motions of the adjacent frames. Doing the matrix multiplication will yield a homogeneous transform that represents the final end effector frame. The last column will yield the end effector position, and this is the same as we saw with the algebraic calculation. So looking at an example of this in Python using HEBI hardware and API, we can calculate the end effector position by initializing the link lengths, creating a function to calculate the homogeneous transform if we know the angles of the actuators, constantly getting feedback from the robot position, and then final position can be pulled out with some matrix indexing. So this is me moving the 2 degree of freedom arm and an output plot of the arm's updated position. HEBI has libraries that make it easy to build any open chain robot. Here's the API calling the forward kinematic function with an arm built out in text formatting. So thanks for watching, and visit HEBI Robotics to learn how our product can help with robotics research and be used as a tool for robotics development and education.